Nice. So this is the last mini lecture on the book in this chapter, and we're going to talk about context dependence. Oops, we have an eraser. Context dependence. So far we've sort of defined what competition is. We've classified it into all these different classes: indirect, direct competition. We've talked about how it's asymmetrical, and sometimes one species is much more negatively impacted than the other, how this can lead to sort of character displacement, niche partitioning, and then we've done a little bit of Lacka-Volterra math to look at when we might expect species to have competitive exclusion versus coexistence versus sort of bistability, where one species dominates depending on starting conditions. But one of the key ideas we've covered this whole semester is that ecology happens nested in an interconnected network, right? That when we examine interactions on their own, we often miss all of the cool ecological connections that are at play. And I think the main idea of this last mini lecture is that we can idealize systems where the species with the lowest R star value for silica outcompetes and competitively excludes another species. But in the real environment, things like abiotic variation at the landscape level, other biotic interactions, and temporal variation change all of these competitive dynamics we were talking about, right? And these are a huge part of, in addition to some of the things we've talked about in the last two mini lectures, things that maintain coexistence between species that might competitively exclude each other, right? Okay, so let's talk about some examples here. The first one I want to talk about is other biotic interactions. Your book does a really nice job, gives a really great example of ragweed. So ragweed is this really common weed in the Northeast, and it's a really strong competitor, right? It grows quickly, produces lots and lots of seeds. They grow to a high density, has a really low R star value. And ragweed in isolation, when we do experiments in the lab, outcompetes many of the plants around it. But when we introduce the ragweed flea beetle, it diverts its resources towards defenses. It also has slower growth because this herbivore is consuming its photosynthetic tissue, and this can actually change competitive outcomes, right? So you can imagine a situation, outcomes. You can imagine a situation where you might predict that ragweed should competitively exclude all of its sort of co-occurring species, but if this flea beetle has outbreaks like we talked about in the population section, or varies across the landscape like we'll talk about later in the semester, then we could imagine coexistence being sort of patchy. In some places, ragweed outcompetes and competitively excludes other species. In some places, the flea beetle is so strong that it shifts the competitive dynamics totally, and other plants competitively exclude ragweed. And in some places, we enter this sort of stable equilibrium where species can coexist, right? And so herbivores drive this in plant competition. Predators drive this in animal competition. Competition is shaped by these other biotic ecological interactions. The other thing that's critical to know is that competition varies, the strength of it and the direction of it varies with abiotic conditions. So early on in chapter 14, your book talks about some other experiments by David Tillman and colleagues looking at the relative effect of competition across an abiotic gradient. And they showed that some grass species, for example, are really strongly impacted by competition with co-occurring species, except when you add fertilizer, or except in really high light environments. And the idea here is that because competition is driven by limited resources, and population sizes, competition is low when resources are really high, right? So in places where we add fertilizer, for example, competition can be really low for a small portion of time until those plants grow in and take up all those nutrients, right? And you can imagine situations where abiotic variation could shape all sorts of competition, right? It could shape all sorts of the availability of those limited resources. For example, in really silica-rich environments, you wouldn't expect competition for silica in the shells of diatoms to be all that strong, right? The last one that your book talks about, and this is important, is called temporal variation, but specifically temporal disturbance. And disturbance can play with species' adaptive traits to favor different competitors in different scenarios. And one of the coolest ideas here is that some species do really well after disturbance. They're really great at dispersing into disturbed habitats, but they're not as strong competitors, right? And so immediately after disturbance, these really strong dispersers move in, and then slowly the slow dispersing competitors move in. And this idea leads to this thing called the intermediate disturbance hypothesis. Which predicts that diversity in some communities, species diversity, can actually be highest not when disturbance is low, but when it's at intermediate levels. Because this intermediate disturbance removes strong competitors, allows weaker competitors that are better dispersers to come into the environment, and it needs to happen frequently enough that dispersers can get in, but not so frequently enough that it totally removes those strong competitors. And so the big take home of this mini lecture, right, is that competition isn't fixed. It can be changed or reversed by consumers, abiotic conditions, and disturbance, and that these asymmetries that we talked about are constantly in flux, right? Context dependence is one of the central ideas of modern ecology, and I think our field is really heading towards this direction of understanding under what contexts can we predict ecology, and how much do we need to know to predict the outcome of ecological interactions. So under what contexts can we predict ecological interactions and what are the important contextual drivers? This especially speaks to shifting climates, and your book talks a little bit about that. I'd love you guys to read those descriptions of shifting rodents on mountains, for example, in response to climate change. But that is also part of this temporal variation in abiotic and biotic contexts. So thanks for sticking with me. It was a little bit of a short lecture series this week, but I really have been enjoying putting these together for y'all. So we're making our way through the semester. See y'all.